My next topic will be about arrays, and will be about load and store instructions. Now, we know arrays from high-level programming languages. In a high-level programming language, an array is just a data structure. We call it homogeneous data structure. Why homogeneous?
Same type.
Yes, all the elements in the array are of the same data type. Same data type, it means they are of the same size. And therefore, the array can be indexed. Okay. Now, once an array is allocated, its size cannot be modified. Now, you can free the array and allocate another array, but you have to copy the data from one array to another array. Okay, so you allocate the array, its size is fixed, okay, in memory. If you would like to increase its size, you have to allocate another array, okay, with a larger size. So the size of the array cannot be modified once you have allocated the array. Now, the base address of the array is the address of the first element in the array. This is something very important when you are dealing with arrays of the assembly language. We need to know what's the address of the array, the address of the first element of the array. So we call it the base address. Now, the nice thing about arrays is that it can be indexed. In high-level programming languages, we can use an index to access the array elements. We can just go to any element at any index inside the array. But in assembly language, we don't use the index. We have to calculate the address. So in high-level programming languages, they hide that you don't deal with the memory addresses. In the case of assembly language, we deal with memory addresses. So when you are programming in assembly, the address of any array, element, okay, can be computed. So what we do is that we can do address calculation. We use instructions to calculate the addresses of the array elements. So this is how we deal with arrays in a high-level programming language. So you allocate the array. The array can be allocated either statically or dynamically at runtime. You can index the array, okay, to access any element inside the array. But you don't really calculate the memory addresses directly. Okay, so this is done by the compiler when the compiler translates the program from high level into assembly language. Of course, the compiler has to generate the instructions that will do the address calculation. Now, because we are programming in assembly, we have to understand how to do address calculation. Address calculation is very important when you would like to index the elements of an array. So how do we allocate an array? An array is just a block of memory. So all what you need to do is just to allocate a block of memory. In fact, if you would like to allocate any object of any data type, it is just a block of memory. Okay, so this is basically what you need to do, because you are just allocating blocks of memory to these objects. And an array is just a block of memory. We can allocate the array either statically or dynamically. I'm going to show you how this is done in the next few slides. Okay. So let me here show you first the static array allocation. Static means that the allocation is done statically by the assembler before it is allocated in the static area of the data segment. And the array will exist at the beginning of the execution of the program and throughout the execution of the program. This is the meaning of static allocation. So we can allocate it in the static area of the data segment. You define a label, you define a type, and you can have a list of values, okay, as shown here in this slide. So let me use my highlighter. So label here is just the label of the array. Dot type here, this is a directive that will specify the type of each element in the array. And you can have a list of values like value 0, value 1, and so on. And these values are separated by comma. So this is how you define an array statically. It is just a list of values. Now, here are some examples of static array definition. This is one way. Another way is to use the dot space directive. I have some examples. So, for example, array 1, this is just a label. Dot half indicates that each element is a half word. And we know that half word is 2 bytes. It means that each element of the array is 2 bytes. So we have here two values, 20 and -1. These are the two values. So this will be an array of 2 half words, and the elements will be initialized in memory. So this is one way of defining the static array. And the elements are defined, the values of these elements are defined initially before the program starts execution. So you can allocate the array, and you can define the values of these of the array by just having a list of values. Okay. If you would like to have an array and all the elements are initialized to the same value. Okay, so if you would like to do it like, so the second array here, array 2, is .word. If you can turn off your, okay, thank you. So the second array, array 2, is .word. Now notice that this .word, yes, Salman, you have a question?
By mistake.
Right, no problem. So notice that array 2 is an array of words. Notice that .word here means that 4 bytes per element. Now the value is 1, and there are 5 elements in the array. So the colon 5, when you write colon followed by 5, it means that you have an array of 5 elements. These are 5 words, and all of them are initialized with the same value, which is 1. So this will be, this is the syntax if you would like to allocate an array and all the elements are initialized with the same value. If you would like to allocate an array but without initializing its values, you use the dot space directive. For example, here array 3 dot space. Here we are allocating space in the data segment, but without initializing this space. And 20 here means 20 bytes. So we are allocating here space for 20 bytes for this array. Now the array can be of any data type, but we are only allocating a block of memory in the static area of the data segment. So 20 bytes, for example, if it was an array of words, then we will have each word is 4 bytes. We'll have 5 elements in the array, and each element is 4 bytes. This will be 20 bytes. If you have it an array of half words, you might have 10 elements in the array, and each element is 2 bytes. This will also give you 20 bytes. So when you would like to allocate an array as dot space, you have to calculate how many bytes you need for this array. So it depends on the element size, how many bytes per element, and how many elements you would like to allocate in the array. But at the end, you just have a number, a single number that will specify how many bytes you would like to allocate in memory for that array, regardless of the type of the array. So when you see dot space, okay, you are allocating just 20 bytes. Okay, so you can allocate any number of bytes, but you are not really specifying to the assembler what are these elements of what data type, are these integers, are these floating point numbers, what's the size of each element. The assembler does not really care. All what it cares is that how many bytes you would like to allocate in memory for this array. So you have to do the math and calculate how many bytes you need to allocate, and you allocate that number of bytes. Okay. If you would like to allocate space for strings, use the .ASCII or .ASCII-Z. .ASCII-Z, it means that there is an extra null byte that terminates the string. So here my label is str1, and between double quotes you can just insert your string. So this is a string, which is basically an array because strings are arrays of bytes. Each character in the string is an ASCII, is a byte, which is an ASCII character. And there is an extra byte, which is not shown in the string. This is the null character because you are using the .ASCII Z. So the Z indicates that there is a 0 byte that terminates the string. Okay. So all of these are examples of static array allocation. Any question about this? So yes.
It's clear, Doctor.
Yeah. So remember that the concept of types, data types, okay, it vanishes when you are programming in a low-level assembly language. All what you are dealing with are just bytes and memory allocation. And really, the assembler does not really care what's the type of the elements inside the array. It does not really matter. Okay, you just say dot space, and you allocate how much space you need for the array. So sometimes you can specify, let us say, dot half, dot word. You can use these to specify the size of each element. But with dot space, really, the assembler does not really care what's the type of element in the array. You are just allocating a block, a certain number of bytes inside memory for the array. Now you can watch the values in the data segment. Okay, you have been doing this since the beginning of the semester. Okay, so you can look inside the data segment starting at a given address, and you can watch the values. What the Mars tool shows you, it shows you as words, and it will show you that the value here at offset 0, at offset 4, 8, and so on. See here means 12, then we have 10 means 16, and so on. So these addresses are shown in hexadecimal. If you would like to see them in decimal, you can uncheck this box and you can see the addresses in decimal. But typically programmers prefer to use hexadecimal for the memory addresses. You can look at the values in hexadecimal. You can check this box if you would like to see them in hexadecimal. Now each word is 4 bytes. Each 2 digits will be a single byte. If we are using the little endian byte ordering, because the Mars tool uses the little endian byte ordering, you can look at these bytes, but these bytes are reversed. Okay. So the bytes are reversed because this is the most significant byte, this is the least significant byte, but the least significant byte appears first, okay, at offset 0. Okay, so we have 1, 4, then 0, 0, then FF, then FF. Okay, so the bytes are reversed inside the word. Okay, inside the word, the bytes are reversed. So you can watch these values in the data segment. If you would like to also use ASCII, for example, when you are dealing with strings, you can check this box and you can see the characters. Okay. Sometimes it's awkward to look at numbers as characters. So this is why you have the option here to see the values. You can see the values in decimal and hexadecimal. You can also watch the characters as ASCII. In addition to this, the Mars tool provides a window here, sorry, for the labels. Okay, so labels here is my symbol table. So it shows the names of the symbols or the names of the labels. So in our previous example, in the previous slide, we have seen that here we have array 1, array 2, array 3, and string 1 str1. Okay, so these were the labels that we have defined in the data segment. So it will show me the labels, and it will show me their corresponding memory addresses. So this is great. I can see what are the addresses of these labels in the data segment, because all of these data are allocated in the data segment. If you use the LA is a pseudo instruction. It means load address. So what this pseudo instruction, what the assembler will do, is going to copy the address of a given label into a register. So if you want to know what's the address of a given symbol, so I call it symbol or a label. So you can use the LA pseudo instruction to load the address, okay, which is from the symbol table, okay, from this table, which is called labels. it's going to copy the address into a register so that you can use this address in programming. Is this clear? So this is the LA pseudo instruction. So all what it does is going to initialize a register with a given address, and this address is taken from this symbol table. Okay. By the way, the symbol table is not just for data. You can also use it for the labels, which are for instructions. And even for instructions, it will show you what are the labels and what are their corresponding memory addresses. So the memory addresses can be in the data segment, they can be in the text segment. You can check both of them here if you would like to take both of them. If you just if you are only interested in the data segment, just check the box for data. But if you also would like to check what are the labels that appear in the text segment, in the code segment, these are the labels of instructions. Check this box, which is called text here, and it will show you the labels and their corresponding memory addresses. So this is the importance of the symbol table. The assembler is going to construct the symbol table. You can view this this table. It is just a window that appears inside the MARS. Now you can allocate memory dynamically. Okay, please interrupt me if you have any question. You can also allocate memory dynamically. This is called dynamic memory allocation. This is very useful. So today, almost all programming languages allow you to allocate memory dynamically, not just statically. So this is one of the functions of the operating system, is to manage memory at runtime. So the OS here, it's the operating system. Okay, so the operating system, one of its functions is to manage the memory. It allocates memory to different programs. I'm not going to go into how the operating system does the memory management, because this is a different course. It's outside the scope of this course. But the operating system is responsible of managing the memory and allocating memory to different applications. So you can have many applications in memory, and the operating system is managing the memory and allocating the memory to these different applications. So you can request memory at runtime. In order to request a memory at runtime, you have to use a system called the system call instruction. And there is a service specifically to allocate memory at runtime. So anytime you use the new operator, for example, in a high-level programming language like in Java or in C++, they use the new operator. Memory is allocated at runtime, okay, when the instruction is executed, okay, or when this statement is executed. In the assembly language, we use a system call, because to obtain memory at runtime, you have to request it from the operating system. It's a service which is provided by the operating system. And the operating system is going to allocate the memory in the heap area, which is the dynamic area of the data segment. So this heap area, you can use it to allocate memory dynamically at runtime. It can grow, it can shrink if you free memory. So you can use it to allocate memory dynamically at runtime. So the heap, it's called the heap. It's part of the data segment. This is the name, heap. It's a part of the data segment. And this part, it can grow at runtime. It's dynamic. It means that you can allocate the memory. You can request memory at runtime. Now, the way to do it in assembly language, you have to use the system call instruction. And you have to use here v0 equal to 9. Notice that you have, this is called service 9 or system call 9. So you have to use this system call. So this is why you have to initialize v0 with 9. So this is load immediate that will initialize the register v0 with 9. Also, what you have to do is that you have to specify how many bytes you would like to allocate dynamically at runtime. So for example, if I would like to allocate 100 bytes, I have to initialize A0. So A0 is my parameter to this system call. It specifies that how many bytes you would like to allocate at runtime. So in this example, I would like to allocate 100 bytes. So the system call is 9. System call 9 means Well, that will be the system call for allocating memory at runtime. This is my memory allocate function, if you would like, or system call. And once you execute the system call, then the system call is going to request, okay, is going to transfer. It's like executing a function that will allocate. So this function is part of the operating system. So the operating system is going to allocate 100 bytes for the program, and it's going to return the address of the block that was allocated on the heap is going to return this address in V0. So once this system call returns, so remember that the system call is like a function call. The only difference is that the function itself exists as part of the operating system kernel, because the operating system is managing, okay, the memory for a given application. So once the system call returns, then we have the address of the block inside the V0. So you know where this block exists in memory because you have the address in V0. Now you would like to save it in another register T0, you can just say the move. Move is going to copy V0 into. Yes, Ali.
Doctor, if it's just an address of the memory, why we are using a register? Why don't we use just a label for that address?
Because you see that this is the array, we are allocating it dynamically at runtime, and we don't even have a label, okay, for that array. It's different from static memory allocation, in which the allocation is done, okay, by the assembler. Okay, so here this array did not exist except after executing the system call. So we are allocating the array dynamically at runtime. It did not exist at the initial execution of the program. It only existed after executing the system call instruction. So only after executing the system call instruction, the array was allocated, and we got the address of the array in memory in a register. So here the address is not really something which is fixed, okay, like a label. The label will be an address which is fixed, okay. It is allocated by the assembler, okay. It exists in the static area of the data segment, whereas here we are using dynamic memory allocation in the heap, which is the dynamic part of the data segment, okay. So there is a big difference. Yeah, although the label is an address, but this address is a fixed address, whereas here the address can be anywhere in memory, and therefore it has to be stored in a register. So we're storing the address we're returning this address in a register. In this example, to be V0. V0 will contain the address, okay, of the allocated block. We can copy it into T0 and we start using it later in the program.
Because it is not fixed, so we can change the address at runtime. That's why we are saving it to register.
Yes. So in the case of a label, the address is fixed, okay, by the assembler. So the assembler is going to map the label into a fixed address, whereas in the case of dynamic memory allocation, the address is not fixed; it's requested, okay, and it's like a variable. And this address is stored in a register, okay? Like we store any variable inside a register, we store also the memory address of the block that we would like to allocate in a register. Is this clear?
Okay. Yeah, it's clear.
Right. So now we can look here at how we allocate dynamic memory on the heap. So remember that the data segment consists of two parts. We have the static area, we have the heap area. This heap area is the dynamic area. So when we execute the system call instruction, when we use the, as we have seen in the previous slide, this was the system call 9 because we have initialized V0 to 9. So this system call is going to allocate a block on the heap and allow the heap to grow at runtime. Now you will get an address. So once this system call is going to return, you will get an address. And this address can be whatever is the address of the block that was allocated by the system call function at runtime. So there is a function for each system call. in this case, there's a function for this system called 9. This function is responsible of allocating memory at runtime, okay, dynamically at runtime, and it's going to allocate it in this heap area. So this is the meaning of the heap. Okay, it's a dynamic area on the data segment. And we allocate blocks of memory dynamically at runtime. So only when we execute the system call instruction, the allocation takes place. Okay. So this is why the memory is allocated at runtime. This is why we call it dynamic. So the meaning of dynamic, it means that it takes place at runtime. It takes at runtime. Whereas static, it means it's done by the assembler during the time when we are translating the program. There is a big difference between static and dynamic memory allocation. Okay, is this clear?
Yes.
Right. All right, so let us see how we compute the addresses of array elements. So when you have, let us say, an array in a high-level programming language, you can index it. So the nice thing about arrays is that you can index the elements of an array because all the elements are exactly of the same size. You can say what is the, so we can read any element at any index. You can read the element at any index I in the array. So array 0, we use index 0 to indicate that this is the index of the first element in the array. And then you can use any index I, where I here can be a variable. Okay, that will be the value of the element at index I. Okay, so the index here is I. Now, if you would like to determine the address of this element in memory, the memory address. So I here is just an index. So if you have n elements in the array, these will be indexed from 0 to n minus 1. So 0 will be the index of the first element, and n minus 1 will be the index of the last element in the array if you have n elements in the array. Now, in assembly, we do not index, we address. Okay, we calculate the address because we have to use the load and the store instruction to transfer the data from to read and write memory. So to read and write the elements of an array from memory. So we need to calculate the memory address. So to calculate the memory address in some high-level programming languages, they use the ampersand here to indicate the address. For example, this is used in the C programming language. Okay, so probably most of you have taken the Java. Java does not really use this address operator, but there are other programming languages like C, C++, and other programming languages that use the address operator. So when you would like to refer to the memory address, use this address operator. This will be the address of array of I. So you can refer to the address of a specific element inside the array. Okay, so this is the address of the element at index I. Okay, so the index is I, but this address operator, the ampersand here, is the address operator. Okay, this will give you the address of the element at this specific index I. Now, how do we calculate the address? To calculate the address, we look at the address of the array. The address of the array is the address of the array at index 0. That will be the address of the first element of the array. And then we look at I, the index I, and we multiply it by the element size. So notice that here I'm multiplying it by the element size. I need to multiply it by the element size because the size of the element here can be anything. Okay, for example, if you are dealing with an array of words, then each element will be 4 bytes. So the element size will be 4. So you have to multiply the I here by 4, the index by 4, because each element is 4 bytes, and then we add it to the address, the base address of the array. Now this works nicely if you have a one-dimensional array. If you have a two-dimensional array, for example, if you have a matrix, okay, the matrix will be stored linearly in memory. Okay, I have it here in this slide. Let us take a look at this matrix. Okay, so now here I have the matrix. Now the matrix consists of a certain number of rows and a certain number of columns. Now the rows are indexed from 0 to rows minus 1. And for example, if I have 10 rows, it will be from 0 to 9. So the last index will be rows minus 1. So rows here indicates the total number of rows. And here I have columns. Okay. So these columns are indexed from 0 to columns minus 1. For example, if I have 20 columns, it will be from 0 to 19. Okay. So the last column would be at index columns minus 1. Now, suppose I would like to determine the address of this element inside the matrix. How do I calculate the address? Now, you can refer to it as the address of matrix at index row index I and column index j. Now, how do I calculate? The question is, how do I calculate the address of any element at specific row index I and column index j? I would like to know what is the address of this element. Do you understand the question?
Yes.
This is the question that I'm trying to answer now. Okay, I really would like to calculate the address of the element at row index I and column index j. This is very important because knowing how to calculate this address, we can convert the row index and the column index into an address. So remember that in high-level programming languages, we use the index. Okay, we can use a row index and a column index to index a matrix. However, okay, the way that the CPU works, okay, the processor, okay, the processor has to address memory, so it has to translate the row and the column index into a memory address. Okay, so address calculation is essential if you are programming in assembly. So you have to understand how to do address calculation. Now the compiler does this automatically for you when the compiler translates a program from a high-level programming language into assembly. But since we are programming in assembly, you have to do it yourself. You have to do address calculation yourself. So you have to understand how address calculation is done. This is the importance of this slide. So we start at the address of the first element here at index 0, 0. Okay, so it will be here address of matrix. That will be the address of the first element here in the matrix. Now the question is, how do we store the elements of a matrix in memory? Now memory is linear. You can think about memory as a linear array, okay, of bytes. So the question is, what will be the address of the element here at row index I and column index j? Okay, so this is the question here. So I want really to find what is the address of this element here. I know that the address of the first element at row index 0, 0, it's basically here the address of matrix. It will be the address of this first element. This is where the matrix starts in memory. That will be the address of the first element inside the matrix. In order to do this, you have to, okay, ask this question. In what order do we store the elements of a matrix in memory? In what order these elements appear in memory? Well, we can store the matrix by rows, or we can store the matrix by columns in memory, because memory itself is linear. Now, the way that most programming languages store the matrix, okay, it stores the matrix by rows. So this is called row major order. So first we store all the elements of row 0. This is row 0 here, right? So we store all the elements of this row. So all of them will appear in memory. This is the first row, row 0. And then after that, we store all the elements of row 1. They appear in this order. So notice that row 1 appears after row 0 in memory. So we go from row 0 and then we go here to row 1. Okay. So basically row 1 appears here. Okay, it appears here after row 0 in memory. So the way that okay, the way that the 2D array is stored in memory, it's stored like a 1D array, row by row. This is how the 2D array is stored in memory. Okay, so let me clean up here a little bit. So I'm going to erase this and erase this. So basically, we are storing it row by row, starting at row 0, then row 1, and so on. So we call this row major order. Any question about this?
Can you hear me?
Fine. So now we can say that, okay, how many rows do I have before the row at index I? Yani from row 0 to row I minus 1, how many rows do I have? I need to use my pen tool again. Do you understand this question?
Kinda. I understand.
Okay. So the question is, let me just get my pen tool. So the question is, how many rows appear before row I inside the matrix?
Three.
This is at row index I. How many rows do I have before row I?
I minus 1.
No, it is actually I, because we start at 0. I can be anything. Okay, it does not have to be 3. If I is equal to 3, I will have row 0, 1, 2, so these are 3 rows. If I is equal to 4, I will have 4 rows. Right?
Yes.
So if I have
Yes.
I is equal to 4, I will have 4 rows indexed from 0 to 3. But these are 4 rows. Because we are indexing at row index I will have I rows. Now, each row consists of many, I have actually here columns, is the number of columns inside my matrix. So I have to multiply I multiplied by columns. This will give me how many elements exist in the I rows before this row at index I. So count the number of elements in all of these rows. Count the number of elements. Okay? So these are I multiplied by the number of columns. So we are storing all of them before reaching the row at index I. Now the question is how many elements here I have in this row before in row I before the column index J.
J.
Exactly. I have here J elements. Okay. Can you read my handwriting? Is that clear? Okay. So I have a J element. So I have to add the J plus J. So I multiplied by columns. This will be the number of elements in the I rows plus J is the number of elements in the row I just before I reach this element at column index J. So count the total number of elements here and then multiply it by the element size, because the element size does not really have to be a single byte. You can have an array of words or a matrix of words. Okay, so therefore you have to multiply it by the element size. So this will tell you how many bytes we have before reaching this element at row index I and column index J. And then add this number of bytes to the address of the matrix. This will give you the address of matrix at index row index I and column index J. So this is my equation for calculating the address of any element inside the matrix at any row index I and column index J. So from the index, I can calculate the address. Okay, is this clear?
Yes.
Yes.
This is very important. As I said, address calculation is essential, okay, when you are programming in assembly, because remember that the CPU has to address memory in order to transfer the elements of a matrix or any array in memory into registers. It has to address, you have to calculate the address in order to load or to store. I'll talk about load and store instructions, okay, maybe in my next lecture, okay? So this is how we address, okay, the elements of a matrix. Right. So for example here, okay, just going back to the previous slide. Okay, so if you have a 2D array, let me go back to my highlighter here. If you have a 2D array, okay, so I have here a matrix and it has a certain number of rows and a certain number of columns, then you can say that the total number of elements will be rows multiplied by columns. So you have to multiply rows by columns to calculate the total number of elements. And if you would like to calculate the address, okay, of the element at row index I and column index j, you have to multiply I multiplied by the columns, add to it j, multiply the result. This will become the number of elements, okay, before this one at row index I and column index j. Multiply this number of elements by the element size. This will give you the number of bytes. Add it to the address, the base address of the matrix. This will be the address of the matrix at index 0, 0. This will give you the address of the matrix at index ij. So here, for example, okay, if you like to allocate a matrix statically, okay, let us say a matrix of words, it's initialized to 0 and you have 200 elements. Okay, so these will be 200 words. Yani, for example, it might have 10 rows and 20 columns. So 10 multiplied by 20, this will be 200. So this is how you allocate the matrix statically. If you would like to allocate the matrix dynamically at runtime, you have to multiply 200 by 4 because each word is 4 bytes. So this will give you 800 bytes. Okay, that's the block of memory for this matrix that has 10 rows and 20 columns. If you would like to calculate the address of matrix 1, 5, you have to multiply 1 by 20 because you have 20 columns, add to it 5, that's the column index. So this will give you 25 multiplied by 4, this will give you 100. So therefore, the address of matrix at row index 1 and column index 5, it will be the address of the matrix plus 100 bytes. Okay?
Doctor, can you repeat the last thing? Address.
So basically, it is just using the equation that we have seen above. So we're just using this equation, okay? So in order to calculate, let us say if you have I is equal to 1 and j is equal to 5, so you have to multiply I by the number of columns. The number of columns is 20, okay? So notice that, let me use my pen tool. This is I, which is equal to 1. This is j, which is equal to 5. So I here is multiplied by the number of columns. The number of columns here is 20. Add to it plus j. So you have 25 elements. 20 multiplied by 1 plus 5 is 25. You have to multiply it by the element size. The element size is 4 bytes because it's an array of words. Okay, it says here dot word. So word means 4 bytes. So 25 multiplied by 4, this will give you 100 bytes. So to calculate the address of this element at row index 1 and column index 5, you have to add 100 to the address of matrix. Is this clear?
Yes.
Okay, good. So this is basically how we do address calculation when we are dealing with matrices. Now, the array will exist in memory. And what we have to do is that we should be able to read and write memory. We should be able to read the elements of the array. We should be able to read any value in memory. And we should be able also to write memory. So in order to read memory, we use the load instruction. In order to write memory, we use the store instruction. And in order to load or to store, you have to specify the memory address. Okay, so the memory addresses should be specified by the load and by the store instruction. So load means that we transfer the data from memory to a register, whereas the store instruction means that we transfer the data from a register to memory. So we are writing memory. This is the meaning of store. And you should always specify the memory address when you are using the load or the store instruction. Okay, so let me talk more in details about these two instructions, load and store. So we can load a word, we can also store a word. So the load word instruction is LW. So it means that you would like to load word. Word means 4 bytes in the MIPS architecture. This is the meaning of a word. For example, if you would like to load an integer, you use the load word instruction. Yani, for example, if you have an array of integers and you would like to read an element, okay, of the array, which is in memory, then use this load word instruction. So you specify the memory address. The memory address is specified by source register RS and an immediate constant, which is part of the instruction. So the value of register RS will be added to the immediate constant, okay? And this is how we compute the memory address. And we load the word, we load 4 bytes. We read 4 bytes from memory into destination register RT. So RT here is my destination register in the case of the load word instruction. In the case of store word, we are going to write to memory. Notice the syntax. So we are going to store 4 bytes in memory. So we are going to store the value of register RT. RT here consists of 4 bytes. And we are going to store the value of register RT in memory. So we are writing to memory. So the address is calculated exactly the same way. It's the value of register RS plus the immediate constant. This is how we address memory. Okay, so this is how the address is calculated by load and by store. It's exactly the same way. We call this base displacement addressing. Okay, this is the addressing mode, which is used by the MIPS architecture. So register RS, we call it the base. Okay, it contains the base address. For example, it might contain the address of an array in memory. So we call it the base address. And immediate is just a constant. We call it the displacement. So we specify the address using 2 values, the value in register RS, which is called the base address. And also we specify a constant here, which is the immediate, which is called a displacement. Now, this immediate can be signed, it can be positive, it can be negative, and it is sign extended. Okay, it is signed extended before we do the addition to the base address. So the base address is stored in register RS. It consists of 32 bits because we are talking here about 32-bit registers and the 32-bit architecture. And we add to it the 16-bit immediate. So the 16-bit immediate must be extended to 32 bits before we do this addition. So sign extension because the immediate is signed. So this shows the base or displacement addressing mode. So the instruction here, the load or the store instruction is of the immediate type. So there is a unique opcode that will specify whether the instruction is load word or store word. RS here will be the source register containing the base address. We add to it the immediate. Notice that there is an addition here. So the value of source register RS, the value will be the base address. I'm showing it in green. And we add to it the immediate, which is a constant, which is part of the instruction. So this is how we compute the memory address. Now we address memory, okay, and this is a memory word. So we transfer a word from memory into destination register RT. In the case of a load, we are reading memory. So we are transferring the word from memory into destination register RT. In the case of a store, we are writing memory. So we are transferring the word from register RT. So RT becomes a second source register in addition to RS, which is a source. Also, RT will be a source in the case of the store instruction. And we are writing memory. So 4 bytes are written in memory in the case of the store word instruction. So this is the meaning of the load word and the store word instruction. Here's an example on load and store. Suppose I would like to translate this statement where A is an array and it is an array of words. Okay, for example, an array of integers where each integer is a word is 4 bytes in memory. So I would like to compute A1, which is A2 plus 5. So how do I translate this statement into assembly? I'm assuming here that the address, this is the base address of the array A, is stored in register T0. So T0 contains the base address of the array A. Okay, so any volunteer would like to tell me how to translate this statement?
Yes, Doctor. First, we load the value of A2 to a register using load word. Then
exactly, yes.
Then the
notice,
will
yes,
be 8.
Yes, you are correct. So notice that we are reading the value of A2 here, and the value of A2 exists in memory, right? And the value of A2 is a word. So we have to use the load word instruction. So anything that appears on the right-hand side of the assignment operator, it has to be read. So therefore, we have to read the value of A2. And this array exists in memory. So the value of this element exists in memory. And it is a word, so therefore we have to use load word. Okay, so how do we compute the address of A2? In order to load the value of A2, we have to specify what's the address. Amr, you said we are going to use load word. So yes. What is the address of A2?
The address of A2 is the base and with offset 8 because it's 4 byte. The word 4 byte, and we move for 2 addresses.
Excellent, excellent. So we know that the base address of the array exists in T0. And the offset, or the, if you would like, the displacement will be 2 times 4 bytes. So the index is 2 here, right? We have to multiply 2 by 4 because each element in the array is 4 bytes. So 2 multiplied by 4 is 8. So we have to use a displacement of 8. So it will be a displacement 8, okay, from the starting address of the array. So we use T0 plus 8. This is how we load. After loading, what do we do? So we can load into any, let us say, temporary register, into any register inside the CPU. Now, once we have the value of A2 in a register, what should be done next?
Add 5.
Yes, add immediate. So what we have to do is that we have to add the constant 5. Yes. This is a very simple example. Now, once we have added the constant 5, we can place the result in any register inside the CPU. Notice that the calculation is done inside the CPU. What should be done next?
Store the value in A1.
Yes, we have to use the store instruction because we are going to write, okay, A1. So anything here that appears on the left-hand side of this assignment operator should be written. And we know that this array element exists in memory. So therefore, we are going to write A1 in memory. What's the address of A1?
It's the base multiply 4 by 1.
Yes, so it is T0 plus 4. So the 1 here is multiplied by 4, so the displacement is 4, so it's T0 plus 4. Okay, great. So now we have the first load instruction, okay, that's going to load the value of A2. Notice that I use the displacement here 8. This is the base address. So this is how we specify the address to a load instruction. Now the value is loaded into T1. Okay, so T1 contains the value of A2. Next, we can use add immediate to add the value of T1 plus 5 to compute the right-hand side, to compute the value of this expression. We place the result in T2. You can actually use any register. You can also overwrite T1 if you want. Okay, so it's up to you. You can use the same register T1 or you can use a different register T2. So this will calculate the value of A2 plus 5. And we have the result in T2. We have the value in T2. And finally, what we have to do is that we have to store T2 in memory. And the address will be 4 plus T0. This will be the address of A1. Now, when we index, okay, we index it starting at index 0, then 1, 2. But when we address, we have to use the displacement, correct displacement, okay, in order to load or to store. So in the case of the store instruction, the displacement is 4 in this example. I can show it graphically here. So notice that the index here of A2 and A1 should be multiplied by 4. And we know why. Okay, we know why. Because already you have mentioned this, because each element of the array is a word, and the word is 4 bytes. So therefore, we have to multiply by the size of a word, which is 4 bytes. Remember that memory is byte addressable. So what we need to do is that we need to calculate the number of bytes, not bits. Okay, so it's not bit addressable, it's byte addressable. So when we specify the address in memory, it's the address of a byte. So when we would like to, let us say, load a word, we have to specify the address of the word, which is the address of the first byte of the word. Okay. This is shown here. Okay, so what we are doing is that we have this array in memory. This is the array A. So this is the address of the array A. So my array exists in memory. It starts at a given address. So what I need to do is that I need to load the value of A2 from memory. So I'm going to use the load word instruction because I need to read 4 bytes, not just 1 byte. So this will be at address A plus 8. We place it in register T0. So T0 exists inside its CPU. Yes, Khalid, tfadal.
Can you repeat the first part because I didn't hear you very well.
So what I'm saying is that my array exists in memory. Okay, this is what I was saying. I was saying that my array exists in memory. So the first instruction was load word. Okay, so it is a load word because I need to transfer 4 bytes. Each element of the array is 4 bytes. The address of A2, it's the address of the array A plus 8. Okay, so we have added here 8, okay, to calculate the address of this element of the array. So we are going to load, we're going to transfer the value of A2 from memory into a register. So here I'm using register T1. So the value of A2 now will exist inside the CPU, inside register T1. It consists of 4 bytes. Then we have added, we use add immediate here, add IU to add 5 to the value of A2, place the result in another register T2. And the third instruction here is a store word. Notice that store is going to transfer the value of a register into memory. It's going to write. Notice the direction of the arrow. So we are writing memory. So we are writing the element A1 in memory, and this will be at the address of A plus 4. So this will be the address of the element at index 1. So we always multiply the index by 4 because the array is an array of words. Okay, each element inside the word is a 4-byte element. Is this clear? It's a very simple example.
Yes, clear.
Okay, good. You can lower your hand, Khalid, if you are done. You can press on the hand and okay, good. So what we have seen in the previous slide is load word and store word. But suppose I don't really want to load a word. I really would like to load a single byte or a half word. So we have instructions for these. So the MIPS architecture defines a byte to be 8 bits. This is how the byte is defined. In fact, all architectures define the byte in the same way. So byte is universally defined to be 8 bits. So this is the meaning of a byte. So whether you are using the Intel architecture or any other architecture, byte means 8 bits. And memory is byte addressable. word is defined as 4 bytes, which is 32 bits, and there is half word, which is 2 bytes, which is 16 bits. So if you want to load a byte, you have to use the load byte instruction, LB. If you want to load a half word, you have to use the load half, LH. Okay, this will be 2 bytes. If you want to store a byte, you use the SB, okay, store a single byte. And if you would like to store a half word, use store half, okay, SH. So these are instructions which are provided by the MIPS instruction. Now, when you load a byte, into a register, remember that the register is 32 bits. So each register can store 32 bits, but the byte is only 8 bits. So when you are loading a byte from memory into a register, you have 2 choices. You can look at the byte to be signed, and you can use sign extension to the byte. So you have to fill the upper 24 bits of this register. So look at the most significant bit of the byte, and this is what we call the sign of the byte. So if the byte is a signed integer, it has to be sign extended. So LB here, load byte, what it does, it sign extends the byte. It reads the byte, okay? It looks at the byte as if it was as signed. So therefore, it's going to be, it has to sign extend the byte. This is the meaning of LB, load byte. Now, if you want to do 0 extension to the byte, okay, you can use load byte unsigned. So if you have a byte which is unsigned, which can never be negative, then you have to do 0 extension. So for this reason, okay, the MIPS architecture has 2 load byte instructions. It has load byte that will do sign extension for the byte, and it has load byte unsigned. This will do a 0 extension to the byte. Okay, so you can choose, do you need to do sign extension or 0 extension? So you can choose between these 2 instructions. In the case of store byte, we are storing the byte in memory. So whether the byte is signed or unsigned, the same instruction can be used to store the byte in memory. Okay, so store byte is going to store only the least significant byte of a register in memory. Okay. Now, in the case of load half word, okay, we have load half, we have load half unsigned, LH, and we have LHU. The difference between these 2 is that whether we do sign extension or we do 0 extension to the half word. So if you would like to use sign extension, if your half word is signed, is a signed integer, then use load half. Okay, and this will do sign extension. So the most significant bit, this bit here, okay, in the half word will be sign extended. Whereas load half word unsigned, LHU, is going to do 0 extension for the half word. So the half word is unsigned, and therefore it has to be 0 extended. So again, we have these 2 instructions, okay, and depending, of course, on your program, what type of data you are dealing with, you can do sign extension or 0 extension for the data, for the half word. If you would like to store a half word, just use SH, and this will store the least significant 2 bytes or 16 bits. It will store 2 bytes, which are the lower 2 bytes of a register. Is going to store them in memory. So we only have 1 store half word instruction, and it does not really matter whether the half word is signed or unsigned. It is just storing 2 bytes in memory. Okay, regardless whether these 2 bytes are signed or unsigned, it works exactly the same way. Okay, for both types of data. Okay. So these are additional instructions that are also provided by the MIPS architecture, and this is a list of load and store instructions that we have seen. Now, all of them are of the immediate type. You can see the I-type format. Each one has a unique opcode to distinguish between all of these load and store instructions. So load byte, you can see the opcode here is shown in the I-type format. Load half word, I have load word. There is load byte unsigned, load half word unsigned. Okay, so all of these are load instructions, and we use RS to specify the base address. We use the 16-bit immediate to specify the displacement, and the data is loaded into register RT. If you are loading a byte or a half word, the data must be extended. Okay, it must be extended. Whereas load word, the data consists of 4 bytes and it's going to fill the complete register, 32-bit register. In the case of store byte, store half word, and store word, we are writing to memory. Notice that these have unique opcodes. These are the opcodes of these instructions. Of course, you don't really have to memorize these opcodes. Nobody memorizes these opcodes. You can look up these opcodes in a manual. So those who would like to implement the instruction set, would like to design the CPU, or would like to write an assembler for doing the translation from assembly into machine code or machine instructions, they can look up what are the opcodes of these instructions. Okay, so you can look up these opcodes and you can do the translation if you'd like to do it by hand, or you would like to write an assembler for doing the translation of these instructions. So remember that store is going to write memory. Okay, the address is the value of RS plus 16-bit immediate, exactly the same way that we calculate the address for a load instruction, but we are going to store the value of RT in memory. In the case of store byte, we are going to store only 1 byte of RT in memory, which is the least significant byte. In the case of store half words, we are going to store 2 bytes, the least significant 2 bytes of RT in memory, and store word is going to store the 4 bytes of RT. The complete register RT will be stored in memory. This is the difference between these different instructions. And the addressing mode is called base displacement addressing. And what it does is that we calculate the memory address by adding 2 values. The value of RS, which is called the base address, plus the immediate constant, which is called the displacement. Okay. Now, if you want, you can use RS as register 0. Okay, then the value of the memory address will be just the immediate. If you specify RS to be register 0, then the address will be the immediate. Okay, so this will be absolute addressing. And you can choose the value of the immediate to be 0, then the address will be the value of RS only. And this will be called register indirect. In other words, if you don't really need the immediate, you can make it 0. And it becomes register indirect. Okay, so the addressing mode is called base displacement, but we can choose if RS is register 0, or we can choose if the immediate is the constant 0. Okay.
Doctor, can you give us an example or just repeat it? If RS is register 0 and last one.
Well, let me show you. I do have some examples. Let me show you examples how we can, let us say, write loops, and we'll see how we can use these addressing. It's common to use immediate equal to 0, okay, which is called register indirect. Okay, if there is no immediate, and you have the address in RS and there is no need for an immediate. Okay, then in this case you can specify the immediate to be just 0.